Last time we started discussion on HDDs. We discussed 3 different variants. One was status checking, polling versus interrupts. We said that polling is wasting a lot of CPU resources. We could instead use interrupts. We discussed about programmed input-output versus DMA. So CPU doesn't have to get involved with data manipulation or transferring the data. DMA can do that. And finally, we looked at special instructions like in and out versus memory mapped input-output, where the peripherals are also expressed as addresses, directly addressable as memory is. We discussed about disks, and we saw that an input-output on a HDD would require a seek, which is moving the track, moving the head across different tracks, rotate where the disk or the spindle will spin, and it will ensure that different sectors get on a particular under the head, and transfer, which is the act of transferring the data itself, reading or writing. Which of them was the most expensive one? Seek and rotate. Usually, both of them are fairly expensive. Okay, so there are a few other considerations for an HDD. So one of them is called track Skew. What do you think this could mean? Before I explain.
Instead of going first seeking and then rotating.
Okay, somewhat similar. So let's say that this was, maybe the head was here. We have currently read 15. We want to now read 16. So maybe the track moves from this to this. The head moves from this particular track to this track. But by that time, because the rotation speed is very high, this would have already moved to 17. So to read 16 again, you'll have to wait for one full rotation. So the idea is to, instead of having them stacked like this, you would have them stacked in the following way. So giving enough time so that this adjacent track, this adjacent sector, could be already like rotated at that particular instance of time. If you move from 15 to 16, you could have come to this one. Make sense? So again, one of those engineering optimizations which can go either way. So there is no definitely one correct way to do this. The other important thing is called zoning. So do each of these contain the same, do each of these sectors in different, for each of these tracks, what is the number of sectors? Is it the same, is it different? In this layout. But, so the density is going to reduce as you move away from the center, right? The sector density, as in, so we have more physical space available. Could we have put 2 sectors there? We could have done that, right? Why don't we do that? Right, so it will make the disk operation slightly more complicated. But then we have, so that is, let's say, the extreme solution. One extreme solution is to have equal number of sectors or for each of the track. The other solution is to have them proportional to the radius r, the number of sectors. And there is a middle ground, which is somewhat better, which is to define some zones. Let's say they contain 3 or 4 sectors, 3 or 4 tracks, or maybe some number. And for each of these zones, the number of sectors per track remains the same. So for the yellow or the orange one, or the skin color one, we'll have equal number of sectors for both of these tracks, and similarly for the blue. Okay, cache. Do you think cache?
That number of sectors are same in this one.
They should be same. Maybe they're not depicted in this picture.
The number of sectors in skin color and blue color is same, but our aim is to increase.
Yes, that is what I'm saying. Maybe it's not shown it pictorially correct, but maybe for the bigger sectors, for the tracks which are further away from the center, you can maybe divide them into 2, something on that lines. Okay, why do we need caching for the disk?
We
So that's why we can use cache. But why do we need cache?
Because of reading everything.
Because it's very slow. Can we cache both read and write? Okay, give me an example of where you'll cache some reads. Let's say if I am reading block sector 16, which other sectors do you think would be useful to read? 17, 18 or something on the vicinity, right? Again, because of spatial locality. Because the idea is that if you're reading a particular sector, the adjacent sectors are also very likely to be read. So you can pre-fetch them so that you don't have to, so that you're not demand fetching them. You can pre-fetch them. What about writing? Why would caching make sense for writing?
So instead of putting one byte at a time, like bulk it and then put it.
Right, so that is buffering or buffer the writes. The other way to look at it is that for the OS or for the logical entity which is trying to write, you immediately say that I've written something, but you don't put that content on the disk immediately. You just put that in a cache, and you can then you can return as soon as possible so that the input output is not blocked. And after some time, like whatever time it takes to physically write to the disk, you can take that. Make sense? Okay, so we'll be studying schedulers even for disk now, as you would expect it. Have you studied these schedulers for disk in the architecture course? No? Are you sure? Elevator algorithm. Okay, this begs a simple question that if we have a stream of requests, in which order should they be served? Let's look at first come first serve or FIFO. So let's assume that the seek plus rotate is taking 10 milliseconds and transfer is taking 100 megabytes per second, which is order of magnitude quicker than seeking plus rotating time for smallish kind of requests. So let's say these are the sector numbers that we want to read. This is the order in which they are requested. So 3 lakh 1, 7 lakh 1, and so on and so forth. What is the approximate time taken to read these 6 sectors? Yeah, 60 milliseconds, given that transfer is order of magnitude quicker than seeking and rotating. What if we change the order a little and we instead have something like this? 20, right? So seeking and rotating to reach this point, seeking and rotating to reach this point. And then the immediate requests are almost free. You don't have to do anything. You still might have to do a rotation, but that's going to be negligible compared to the full rotation seeking. So does it make sense to swap the order of, or change the order of requests at time? Right. So where do you think this scheduling will be done? Is it done by the OS? It is done by the disk? OS? So OS would make sense because we've been, firstly we're studying OS. Secondly, we've been looking at, all of the scheduling has thus far been done in the OS. But does the OS know the intrinsics of the disk? Does it know how the sectors are divided? Does it know about zoning? Or does it even need to know about the zoning?
No, because it will be numbered in sector.
And what if it's instead of HDD, it is something else? Does the OS know about that? No, right? So this is an interesting thing. We can have a scheduler in the OS also. We can have a scheduler in the disk also. Both of them trying to do their own optimizations. But how does a disk have a scheduler? What component does it now require? What computing component does it require to have a scheduler? Processor. So typically, disks have something called a disk controllers, which would be a microcontroller or a processor. And for caching, what do we require? Memory. So disk by itself is now a computer. It has its memory, it has its scheduler, and it has its own processor, and of course, it has some storage space. Okay, then we can come up with some other algorithms, like shortest seek time first. The idea is fairly simple, that you choose the request that will take the least time for seeking. So seeking is moving across tracks. So let's say the head is currently at 30. Should the next request that you want to serve, so we have got 2 options, 19 or 7. Which of them do you think will be chosen? 19, right? Given that 19 is closer in terms of the seek required compared to 7. It's a fairly simple choice, you save some time. will it have some disadvantages using this algorithm? What? Why will it have starvation?
If you put in a request for closer short
Right.
and maintain the longer distance.
Right. So imagine that you're at currently at sector 30. You want to access 7, but the requests which are coming are 7, 8, 10, 20, 32, 21, 33, something on that lines. So if there are enough requests of these closer sectors which require fewer seeks, then the farther away sectors will never be serviced. So they'll be effectively starved.
So like all of them all the requests are the same.
So if all of them are in the same track, then they have the same seeking. Then what is the difference between them? Rotation, right? So that's going to beg the next question in fact. So the head is currently at 30, and the next choice is between 16 and 8. Which of them would be chosen? Head is at 30. Choices between 8 and 16. 16 makes sense because 16 is closer, right? Closer, but it requires fewer seeks. But it requires more rotations. So that is why shorter seek time first is not a fully complete algorithm because it's only looking at seeking. But we also have a rotation period. So 8 can in fact be a better choice given that it doesn't require any rotation, maybe a very few rotations. So this algorithm is called shortest positioning time first, which takes into account both the seek time as well as the rotation time. Okay, so now we come to the scan algorithm or the elevator algorithm. So this is similar in concept to the way we board the elevators. Like there are multiple people, we want them to be serviced. The elevator is a common platform which wants to service. How does the elevator service request? Does anyone know? Or how does this particular elevator service request? Which is in a campus.
It fixes a direction and stops at the close.
It fixes the direction, right? So let's say it will only go in circular. So many times, let's say if I am on floor 3, someone from floor 2nd wanted to go down. But if the lift was going up, it will still continue to go up. From 2nd floor, it will come to the 3rd floor and then take all of us together down. So that's the simple scan or elevator algorithm. That you sweep back and forth from one end of the disk to the other, serving requests as we go. So let's say we start from the outside of the disk. We move towards the inside of the disk. We service all the requests that come in our way, and then we do the opposite direction. So we then start from the middle of the disk and then go outside, service all the requests that were there. What do you think are the pros and the cons of this? Okay, what are the advantages? So it will be probably much more fair compared to the previous algorithms. The problem starvation would be largely reduced. Okay, what are the cons?
It's not optimal.
Why is it not optimal?
So you might
We can define a workload where there is once it starts going to the other end, I start request at this end. Basically, you have to go the entire way and then come back and so on.
Okay. So one simple way to think of this is that this is slightly different from the elevator problem that we were discussing before. Because the elevator problem does not require you to take, so like when we're in the elevator, we are supposed to be taken from point A to point B. But in the disk, we only want the disk, you to be, that particular sector to be read. So this is one difference between them. And con is that it's going to favor the middle tracks more. Because you go from the outside to the inside, and then from the inside to the outside. So by the time you reach the outside again, you have read the middle track twice. And similarly, the inner track has only been read once. So while it's more fair compared to the previous algorithms, it's not still completely fair.
So how does it scan the one particular line?
It just moves in one direction. The head will only move in one direction, and it will keep on servicing requests, and then it will come back. So it goes from the outside to the inside, and then comes from the inside to the outside.
So does the head have to, like, can it write and read at the same time?
Can it write and read at the same time? I don't know, and I don't think so.
So
I don't think so.
So writing might be a problem. Like if I have to write immediately, then if it keeps on reading, then I can write only the end.
Sorry?
If I have a request to keep on writing, but I had a write which came before, will it be waiting till the
Write which came before means.
like,
So let's go back to the.
can we have
Let's start with this.
have one write and one read. So on the way if you get a write, you can write it that time.
So this particular one, so there is a variation of this which is called freeze scan, which will freeze all the input requests at that point of time, and then it will service them. The default one will see that okay, if any new request comes while you're moving, it will then service it. Let's say if I started from 6, I'm going towards 30, and I've serviced 6. At that time, a request for let's say 19 comes, so I'll still service 19 and then go in this direction. So I move from the outermost track to the innermost track, servicing any requests which fall in the middle tracks, and similarly then the other direction.
So like first we service 30, 29, 28, all of them, and then move to the next track, or
Right.
is it zigzag?
So my understanding is that you service all the requests, so you go from the outermost track to the innermost tracks, and whichever requests are in that track, you service them. Okay, so this the regular scan algorithm had a disadvantage that it will favor the middle tracks. There's a simple workaround for that that's called circular scan. So you move from the outside to the inside. You move the head back again to the outside. So you move from 6, 18, 30. Instead of doing 30, 18, 6, you again move to 6.
So we can scan all the sections in the track and one by one. We won't do it until we scan all the sections.
So the rotation, I think the rotation is going to be fairly quick. I think so. Once you're in a particular track, you might as well read all the sectors which are required. But again, that's one particular implementation. There could be multiple ways to understand the same algorithm.
So then it could happen where it keeps rotating in the same track.
It could keep happen that. So that's why this freeze scan is supposedly better, because you freeze. So let's say you started in one direction from 30 to 6. Now you've frozen the set of requests you want to service, because this can again have the problem of, as you're saying, you can have multiple requests in between which are coming. Let's say if I'm, again, this will probably still again favor the middle tracks more. So that's why freeze scan is somewhat better, that you freeze the state of all the requests that you've got, and once you've serviced all of them, then you start accepting the new set of requests.
So, if device C-scan is favoring the middle track.
So no, C-scan is not favoring the middle. This one. So the regular scan, so let's say we start from 6, so it goes to 6, 18, 30, 30, 18, 6. So the middle tracks would be used much more often. Okay, so there's another small thing to discuss. So is it always better to do input-output when it is requested, or is it can be better to wait for some time? So in context of these schedulers, like if we are at this point, let's say we are at the head is at 6, and there is a request for 33. So is it immediately good? Is it a good idea to immediately service 33, or is it a good idea to wait for some time, in anticipation or in hope of that there will be better request on the way, which will lead to globally better solution? Wait, right? But then again, there's an engineering question that how much time do you wait? So that's the notion of anticipatory schedulers. So you'll see that these concepts get repeated again and again in different contexts. So for example, we studied about anticipation and like prefetching, like page prefetching, or even in terms of caching. But even in terms of schedulers, we can do something similar. Okay, so how many of us have studied RAID? Sorry? So everyone studied in Compact? not the electrical people, right? So what is the first thing that comes to your mind when you hear RAID? Sorry? Yeah, anything, first thing. So I was just doing a Google search to look for appropriate images for RAID. This is the first thing which comes. Okay, second thing. Sorry? No, so second different thing. Okay. Unique thing. This Bagon similar to Bagon or this mosquito or insect killer. The third one is this particular thing. Does everyone know what this is? Sorry? 4 disks. It's a RAID controller. So this itself is fairly useful thing to see. So we have got multiple disks and then there is a controller. So why do we require multiple disks? That is the motivation behind using RAID. So it's a classic paper from Berkeley Systems group, Randy Katz and his group, and that's one group whose papers you want to read if you say that you're a systems engineer, you love anything in systems. Some great work has come out of that. Okay, why do we want many disks instead of one? Sorry? Backup or capacity? Backup means redundancy. Okay, what are the other things we require multiple disks for? Sorry? Error correction. Error correction, I would say, is similar to redundancy. We want to add redundancy. Okay, why do we want more disks?
You should be able to read more data.
So one way to look at it is if you just buy the latest MacBooks and you'll be out of space within no time. So you always want more space on the latest SSD devices. You get by default you're getting only 128 GB, right? And if you install some of the Adobe applications, you're out of space very quickly. So you want more space. That's one reason why you want more disks. Capacity, performance. So can using more disks improve the performance in some sense? Unreliability, for reliability or redundancy or but most of the file systems that we've been using, they work only on a single disk, right? Like, can we use the default Linux or Windows operating system to write to multiple disks at the same time to improve the capacity, performance, reliability? No, right? So one way to do this is called JBOD. Anyone knows the full form or can guess the full form? It's a very naive full form. Sorry? Yeah, D is for disks. Joint batch of disks. You close. So OF is of disks. JB is not. Sorry? How do you know? You Google? Okay. It's called just a bunch of disks. So the idea behind the solution is that the application is smart. The application knows how to write through two different disks. But then each application developer would have to spend a lot of effort in the site. So it's not a good solution. The other cool idea which came out of this great paper is that so build a logical or fake disk from many physical disks. The application and the file system don't see this as a fake disk. For them, this is just a regular disk. So this is again virtualization in its purest form. I think this is very, very cool idea. So this is something which just revolutionized computing at that time. So hard disks. Okay, so let's. In a minute, I'll come to why this was a very cool idea. So RAID becomes eventually very transparent to the application, and it's clearly deployable. So it has to be deployable directly. So you don't have to have the application has to become smart or the file system has to be significantly changed. So it's completely transparent to them. And what will the logical disk give us? So what were the goals of why we required more disks? Capacity. So will this give us more capacity? What other were the goals? Performance and reliability. So one trivial way to look at reliability is, let's say in this particular disk we put A and B, and this we have put A and we have put B. So we have just mirrored the content or copied the content of this disk into other disks, so that even if this disk goes rogue, we still have the contents. So that is how we are adding the reliability. So in the Compart course, have you studied all the RAID levels? 0 to 5, including 3 and 2. Okay. Okay. So why do you think RAID became such a successful paper or such a successful technology? And the title is provocative enough. But even if disks are cheap, why did it still become a success? Like hard disks are not reliable. Okay. So if they are not reliable, then how did this become a success? So the central idea to this was it's far more expensive to buy a 500 GB hard disk compared to 1050 GB hard disk, something on that lines. And this was the paper I think in '87. Cheap disks are fairly popular, and this is one of the reasons why Google became such a success. So initially, I think I read this somewhere that Google didn't have petabytes of single disk, but they had thousands of smaller disks, even commodity level disks, like the regular hard disk that we are using. But then they did all the cool stuff in the software layer. Instead of relying on the hardware, they built a virtualization or they built a logical disk on top of that. So come to think of it, it's a fairly simple idea, but that's what many systems paper will be. And you can get commodity hardware components for the same price as few expensive components. And as I was saying, the key idea is to write software to build high quality logical devices from many cheap devices. And the alternative is fairly expensive. You buy an expensive high-end disk, which will again still maybe has 99.99% reliability, but it's still not 100%. So the strategy is fairly simple. You build large and fast disks from smaller ones. Let's say there are 2 smaller disks, and let's say these are the sectors. So these are some storage contents. So now we've doubled the capacity of the disk, of the logical disk. So now you can store from 0 to 200. For the application, now what you're enabling is you're saying that the capacity is 200 units. The application now has no idea of which physical disk it's being mapped to. And we can then add reliability also. So let's say that this particular 0 to 100 units go to this disk, and they're also copied to the next disk. So now even if this disk goes rogue, we still have a backup in the next disk. And similarly for this one. Now for 200 units of storage, how many physical storage units do we have? 400, right? So in some sense, the capacity, while we have doubled the capacity compared to a single disk, but we require 4 more disks. But again, this comes because of the economies of scale. These disks are going to be fairly cheap. So cheap in the sense that again, having a very reliable 200 unit disk is going to be more expensive than 4 of 100 units. That's the key idea behind this. Okay, the problem is now similar to what we've been studying in virtual memory. We want to map the logical addresses to physical addresses. How did we do this in virtual memory? Page table or some kind of hash map or some kind of page table structures, right? How can we do it in this RAID? Do we require dynamic mapping or is it just static mapping? So we go back to the example. So we can fairly easily see that, right? It's only a static mapping that you require. You don't require something to change at runtime. Of course, if something goes bad and you're provisioning and you're adding a new disk, of course you might have to do some juggling. But in the most simplest case, we just require a static mapping. Okay, let's talk about redundancy. Some examples of where we're trying to increase the redundancy is replication, which is RAID. Some examples, again, which we've studied in the OS course, we're trying to reduce the redundancy is code sharing. So this was where, can anyone tell where were we using code sharing? A little louder. Segmentation, right? So we could have some code segment which was not going to be, which was, let's say, read only. So we could have multiple of these processes point to the same code segment, right? So we were then reducing the duplication, or we were doing deduplication. So we're always, in general in systems, we're either increasing or decreasing the redundancy. We're now increasing the redundancy to make things more reliable. Okay, so before we go into the details of RAID, we'll discuss three important things. First is the workload, which is type of reads and writes. So we studied in the previous lecture, we studied about sequentials read and write and random read and write. So we'll be looking at these two particular types of workloads only for now. And what exactly is the RAID? So RAID is a system for mapping logical to physical address. So what do you think is going to be variable across RAID? Like when I mean that R is also variable, what can be the variation in R? Yeah, so different mapping means different amounts of redundancy. And the metric we are going to use is capacity, reliability, and performance. So we'll look into details of the exact metrics. And in RAID, the most important question becomes, which is the mapping question. How do we map logical blocks to physical blocks? Now we'll have different variations of this, which is going to be different RAID levels. Let's look at the workloads for a minute, sequential loads. So in sequential loads, is the transfer going to dominate, or is it the seeking and rotation which is going to dominate? Sorry? Yeah, the answer is there. Can anyone tell me confidently? So why do we require seeking and rotation?
So even if there's less seeking and rotation, it just transfer like an order of magnitude less.
Right.
Sorry?
So like even if seeking and rotation is less in sequential load,
Mhm.
isn't it an order of magnitude more than transfer?
So what happens is that when we talk about sequential loads, we don't talk about a small chunk of data. We generally talk about large chunk of data. So when we're talking about very large chunk of data, then the transfer is going to be big. So we'll look at an example to work out the same. So let's say that the disk speed is, and the answer to the previous one was seeking and rotation is going to be fairly insignificant. So let's say the disk speed is SMBps. And for random loads, the seeking and rotation have very significant cost because you can move the head from any point in the disk to any other point in the disk. And let's say the disk speed for random loads is RMBps. So what is the relation between S and R? S is very, very greater than R, right? For the most general case. So let's work out a simple example. Let's say that the average seek time is 7 milliseconds. Rotation is 3 milliseconds, and transfer rate of the disk. This is the maximum transfer rate of the disk. That's 50 Mbps. Can we calculate S and R for a transfer size of 10 megabytes? What is the value of S? So the first thing to note is that will it be greater than 50 Mbps or less than 50 Mbps? Sorry? So does everyone get the question? Everyone seems a little lost.
So how much data is in one sector?
How much data is in 1 second? Do we even require that?
No, it will be less.
What will be less?
Less than 50.
Less than 50. Why will it be less than 50?
Max we can get, I think.
Yeah, so why is it? What is causing it to be less?
It will rotate.
Rotate, right?
Somewhat.
So the question was the max transfer rate of the disk is 50 Mbps. For a sequential load, will we get 50 Mbps or something less? The answer is something less because even though the seek and rotation are going to be less significant compared to the transfer because it's the big 5, but still they'll have some cost. And the answer can be fairly simply calculated that this is the total amount of disk that you want to access. One seek, one rotate, plus the time taken to transfer this particular 10 megabytes. This is the total time taken. This is the total memory that you want to transfer. So it's going to be approximately 15 megabytes. But it's going to be slightly lesser because of the seek and the rotation.
How do you know we will rotate in sequence?
Sorry? Yeah, because
Binary.
you only want to move the head to the first place, and after that the rotation and seek is negligible because the axes are in order. Okay, what about the random load? What is going to be R?
Now it depends on how many sectors you need to move.
10 kilobytes. That's it. So in random load, we generally think of whatever is the transfer size, that's the size of the sector. That's how we generally solve this problem. That's a single sector read and write. How much time will that take? Because so in sequential load, we're getting the advantage that once you've done the seek and the rotate, all of the blocks are now, all of the sectors are available to you for free. Free means that there is no seeking or rotation required. But in a random load, for each sector access to you that you require, for each of them you'll require a seek and a rotate and then the transfer time. That is why this size is in some sense immaterial. And then give me the approximate answer. You don't require the exact answer.
Instead of 3, maybe we should use 3 by 2. We will use 3 by 2 in the random loads.
3 by 2 means?
Because half we
No. So that is the average rotation time given to you. So this is given as half the time taken to complete it.
It should be the same.
10 kb plus 3.
So the formula remains the same, but the only difference is that instead of 10 MB now you're just having 10. And again, if you've not cleared, let me know now. The difference again, I'll quickly repeat is that, so this could have taken, so this is taking now 10 kilobytes divided by 7 milliseconds, 3 milliseconds plus 10 kilobytes divided by 50 megabytes per second, approximately 1 megabyte per second. Now, for another sector read, it will again take the same time because this same time, which is on the denominator of this, because each 10 kilobyte block is now very physically separated. Whereas in this sequential load, let's say that again you're reading in blocks of 10 kilobytes only, but once you've done the seek and the rotate for the first 10 kilobytes, the next 10 kilobyte blocks or sectors are free for us. We don't require any seeking and rotation. So that's why we can just increase the amount of time, and all the time is directly taken only the transfer. So we can see very clearly that S is 50 times, almost 50 times R in this particular example. Okay, in terms of metrics, we have 3 important metrics. Capacity. So when we are putting in multiple of these disks, what is the overall capacity? Secondly, reliability. So in terms of capacity, if we're putting in more disks, will we get capacity in proportion to the number of disks we are adding? Yes or no? How many think yes? So the question is, let's go back. If we add more disks, in all cases, will the capacity be proportional to the number of disks added? No? Why not? Because of redundancy, right? So we can have cases like this, where though we have added 4 disks, the capacity has been increased only twice because of a factor of 2 redundancy. And the second question is, how many disks can we safely lose? So, is this proportional to the number of disks, or is this independent of the number of disks? Or it depends? So in systems, most of the answers are it depends. You should remember that. and we're going to assume one particular type of fault, which is called fail stop, which is that a disk either works or it doesn't work. And if we know, and you also know that if it's working or not working. So that's the one simple type of fault that we can assume. Performance, how long does each workload take? So if we're adding more disks, will the performance increase or will it remain the same? Why will it increase?
Because if there are multiple parallel threads trying to access the same memory, there might be bottleneck which was covered it to get data before. Now, since there are multiple copies of the same memory,
Right. So each request. So if earlier you had a single disk, now we have multiple disks. You can send you can send data to each of them in parallel. That is why in general the performance can increase. But is the performance increase proportional to the number of disks or not? It depends. So let's look at the simplest type of RAID, which is RAID 0, which in fact is a strange name given that it doesn't have any redundancy. So it's called striping. The idea is that you just put these blocks across multiple disks. So the first block goes in disk 0, the second one goes in the next disk, so on and so forth. Why would we do this? So we have three metrics. Which of them is going to be the best one in this case? Sorry? Performance? Okay, what? Capacity, right? The capacity is doubled, or capacity is increased by a factor of n, where n is the number of disks that we have. So another way to look at this is, so these are the different blocks that we are putting, and so we put them 0, 1, 2, 3 in this way. If we had 4 disks, how would this view look like? So we put block 1 in disk 0, block 1 in disk 1, and so on and so forth. And this one row of this view is called a stripe. Here do you have a doubt?
Block means page here.
So block can mean one logical or one physical entity that you're putting. It could be 1 byte, it could be 64 bytes or 64 kilobytes, depending on what you choose as one. Yeah, depends. Yes. So we have 4 disks. We call this thing as a stripe, this particular row as a stripe. Okay, given a logical address A, can we find out which disk will it go to? Does it seem simple? Let's say if logical address is 8, why should it go to disk 0? Because it goes to disk of A mod disk count. Not discount, disk count. If it was 8, it goes to 8 mod 4, which is 0, which goes to disk 0. And the offset is how many rows offset do we go inside a particular disk. And that's going to be A divided by disk count. Seems fairly simple, right? So this is one way to look at the notion of static mapping, which is in RAID, compared to the dynamic mapping, which we were using in page tables.
Sir, who does the logical to physical address transfer?
So it's the RAID controller, I think. So there is going to be somewhat similar to a controller. This controller is going to be a RAID controller. So the RAID by itself is this is a RAID box where you can physically house the disks, and it will have its own memory and processing, and schedulers also. So now you can also have different chunk sizes. So chunk size equal to 1 means that you write one block or one entity in one disk, and then you move on to the next disk. We can also have chunk size equal to 2, which means you've written 0 and 1, 2, 3, 4, 5, 6, 7, so on and so forth. And so in this case, so chunk size was 2. So 2 rows now constitute a stripe. And coming to the question, so chunk size is 1 for today. Generally, it could be 64 kilobytes also. Okay, now let's come to the analysis, which means that we'll be looking at the different metrics. What is the capacity? Assuming that the capacity of each disk was C, and we have n disks, what is the new capacity? N C. How many disks can fail? 0, right? Electrical folks, are you getting it? zero disk can fail because there is no added redundancy. So let's say that if disk 0 fails, I lose all of this data, right? Because this data is not replicated in any of the other disks. So that is why zero disk can fail in RAID 0. What about throughput for sequential read and write? I've written the answer. Does everyone understand why sequential read and write should be n into s? Because you can write in parallel, right? The speed for each of them, for each of this for sequential read and write was s Mbps, and now you can write n of them in parallel. So the sequential read and write speed now becomes, throughput becomes n process. What about random?
N into R.
N into R, right? Again, it's fairly simple. You can write all of them in parallel. What about latency? If the latency of each disk was D, what is the latency of RAID 0? So does everyone know the difference between latency and throughput? Can anyone give an example from real life situation? So let's talk about making cakes. Let's say that initially only I knew how to make cakes, and I take 1 hour to make cakes. So my latency of making a cake is now 1 hour. Now let's say I train all of you to make cakes, and you are 35 in number. So how much time will each cake now take? Assuming all of us are working independently. 1 hour, right? So the latency remains the same. The amount taken to prepare one cake remains the same. But what is the throughput now? 35. So the throughput has increased in proportion to the number of people who can cook, but the latency of the time required to prepare one cake, that still remains the same. So if the latency of one disk was D, the latency in case of RAID 0 remains D. So that's one important takeaway, that while the throughput will be improved, but latency won't improve. And if you want to remember things, so I'd suggest to remember the cake example. I think generally physical world and cake examples are easier to remember. Okay, let's talk about RAID 1 or mirroring. So it's the first RAID level where we have some amount of redundancy. So the idea is to keep 2 copies of all the data. So we have now 2 disks. Let's say in this example, we wanted to write 4 logical blocks. Each of the block is written to 2 particular disks. And we'll assume that the disks are fail stop, which means that either they work or they don't work. And if they don't work or they work, we know that. There can be other kinds of errors, like one of the sector gives some error, or there is some data corruption, but we'll not look into them for now. So if there are 2 disks, then the view of
So when they don't work, as the whole disk is
the whole disk is not working. So that's a simplifying assumption. Maybe there could be some workarounds for that, but for now. So for example, one simple workaround which I'm thinking right away is that, let's say one sector goes bad, so you can remove that one sector from all the disks. So one block from all the disks you can remove. You can still use this disk which has failed, barring that particular sector. But that one sector cannot be used in other disks also if there is some kind of mirroring happening. So for mirroring or RAID 1, the view looks like the following. So we have now replication across these multiple disks. If we have multiple disks, so this block 0 goes to disk 0 and 1, 1 let's say goes to 2 and 3, so on and so forth. Okay, in this, how many disks can fail? 1.5. Someone said, how many think one disk can fail in this? Okay, 1. Why 1? Good. So all of you have given the right answer. So in the worst case, only one disk can fail. In the best case, 2 disks can fail. So worst case, as in, like let's say that this 0 fails, we still have a copy in disk 1. And let's say in the best case, disk 0 and disk 2 can fail. So we can still have the copies in disk 1 and disk 3. But we can also, if for 2 disk failing, if both disk 0 and disk 1 fail, then that is not going to work for us. That is why, in general, 1 disk can fail. In the best case, n by 2 disks can fail. Okay, what is the capacity given n disks? NC by 2. How many disks can fail? 1 or n by 2? We discussed that. What is the throughput? Sequential write is going to be n by 2 into s. Why is that?
Because we have n by 2.
I have to write 2 times.
Because for each write, we'll have to write 2 places. So in some sense, the amount of parallel writes, so the logical data which we can write can only be half of the maximum capacity. That becomes n by 2 of s. But that is sequential write. What about sequential read? Why is this n by 2 into s?
Why is to ensure?
We don't need to ensure in this. Because only n by 2 have the correct content, right? The other is just a copy. So the amount of addressable capacity, since it was n by 2, you see. So since the amount of addressable contents are only reduced, that is why we don't require. We can't have more throughput. What about random write and random read? Why is random read n by r, n into r?
Because you can read it from the copy and the disk.
So, does everyone understand this? Sequential read was n by 2 into s, whereas a random read is n into r. Why is the difference? What is the difference between sequential and random? So let's go back to this. Yeah, the answer. So what does a sequential read mean? So you're going in sequence, right? Or so sequence means like you're trying to sequentially read the blocks. 0, 1, 2, 3, 4, 5. So in some sense you'll have to skip a block, right? So you'll be still waiting and wasting that particular time. So the sequential read becomes n by 2 into s, whereas a random read you can read from here, anywhere. So you can now read in parallel across n possible disks. So the random read becomes n into r. What about the latency? Sequential write we write both ways. That is why it is n by 2 into s. Sorry? So you'll be okay, I have the analysis system. This is the picture that I made for sequential. I think I made this for sequential read. So let's say you want to read them in order. So you read 0, 1, 2, 3, 4, and 5. So you'll have to basically go through these disks also, right? That is why, because 0 is available on this disk, 1 is available on this disk. So 0 and 4, which are available on the same disk, but still there is an element 2 which you will have to unnecessarily waste, right? So on this disk, they are not, you don't have 0, 1, 2, 3, 4. You have 0 and 2. One of the particular sectors you have to skip. That is why the capacity for read is reduced by half. But your question was? Writing. So for each of the writing, you'll have to write to 2 disks, right? So the parallel writing capacity, the amount of data that you can write is reduced by 2, right? The effective data, the logical data.
So if we store the blocks as 0 and 1,
Right.
then sequential read would
So if you store them as 0, 1, 2, 3, and then again 0, 1, 2, 3. Then in the sequential read, but I don't know why this particular design is favored. I don't know. Maybe there has to be some other trade-off.
So can we do some optimization where I read this 0 reads 0 and this one reads towards the same line? For sequential read. Or sequential read.
Sorry, could you?
Like sequential read first did 0, then 1, then 2. Block number.
Yeah.
So
That's another.
for sequential read we did 0, 1, then 2, right?
Right.
Can't we do 0 and 2 together? Anticipating we need that as well. Buffer and
Yeah, I don't know. Maybe we can. Latency on read and write should be different. Why is that the case?
Because for writing, the latency should be half because we are writing on 2 disks. But reading, we are writing only one.
So I think what will happen is even though you're writing on 2 disks, but in some sense you're writing them parallel. But your point is well taken that one of them could be slower than the other. So the overall time taken, the overall latency should be the max of the time taken by the two, or the max of the latency taken by the two. But it will still be comparable, something between T and 2D. We should just stop at this point.